Okay, here in 2.5 we're looking at implicit differentiation. Implicit differentiation is a derivative strategy that we use when we are looking at a function that has x's and y's that are mixed together in such a way that it is not easy to separate the y by itself, so that our function is in its kind of traditional y equals form or f of x equals form. So our steps for implicit differentiation are as follows. Step 1, we're going to differentiate both sides of the equation with respect to the independent variable. AKA what that means is essentially this is the only calculus step you're doing. You are taking the derivative the same way you always have. Power rule, product rule, quotient rule, chain rules, whatever rule is there, you're still doing those rules. There's just going to be one little piece here, which is that because we are taking the derivative with respect to x, anytime you have a y that you are taking the derivative of, because y is not x, right? It's a different variable. Anytime you're taking the derivative of a y, you're going to acknowledge that you are taking the derivative of that y by tacking a dy dx on the back. And I'll show you what that means here in a bit. Okay, but it's an acknowledgement that we are working with a dependent variable instead of our independent. Okay? Step 2, once you've taken that derivative, actually 2, 3, and 4, it's all algebra. You're going to separate the dependent derivatives from the other terms, which usually means adding or subtracting things to the other side of the equals. Sometimes it's a multiplication or something like that, but I'd say most typically you'll see addition or subtraction. Step 3, if necessary, you're going to factor out a dy dx. So if you do find yourself with more than one dy dx kind of grouped together, you'll factor a dy dx out so that your last step is to solve for the derivative, which is most typically to divide. Okay? And so example 1 here, we are going to find dy dx for 3x squared y plus y cubed equals 18x. And so this is what I mean by mixed variables here. If you notice, we have an x and a y kind of sitting together. We have a y cubed over here. There's no way to easily manipulate this equation to turn it into a y equals blank, whatever your equation is. Like it's too mixed up. And so this is where implicit differentiation is going to kick in. Okay? So step 1, we're going to take the derivative. We're taking the derivative the same way we always have. So as you're looking at the function, you're going to ask yourself, like, what rules do we see here? And then so in this first term, we see that we have two things multiplied together, which tells me that this is product rule. Okay, so product rule 1 is 3x squared. D2, the derivative of y is 1. But then we just took the derivative of a y, so we're going to tack on this dy dx, acknowledging that we are working with the dependent variable right now, that we are taking the derivative of the dependent variable instead of my independent one. Notice the dy dx is not replacing y. The derivative of y is 1. It's just an extra piece that gets tacked on the back. So 1 d2. Then we have plus our 2, which is y. d1, derivative of 3x squared is 6x. Back here we have derivative of y cubed is 3y squared. And then I just took the derivative of y, so I'm going to tack on dy dx. And then the back here derivative of 18x is 18. Okay? And so that's step 1, is just taking the derivative. If you don't like to think of it as tacking the dy dx on, the other way you could potentially think of it is as chain rule, if you prefer, chain rule on these y components. For example, here on the y cubed, we would bring down the 3, leave the guts alone, subtract 1 from the exponent, and then the derivative of y, the derivative of the guts, is dy dx. It always has been, right? Take a look back through all of the notes we've done so far. Every single time we've taken the derivative of y, we've written dy dx equals, because the derivative of y is dy dx, right? That's why we have these dy dx's here. It's just in previous problems, the dy dx has been out front of my derivative because y has been out front of my equation. It's not going to look like that in this particular case because y is no longer out front of my equation. It doesn't say y equals. So my dy dx isn't going to say dy dx equals. Instead, because the y is mixed in with all these other exponents and variables and coefficients, because the y is mixed in, the dy dx is going to get mixed in as well. It's just tacked on the back every time you take the derivative of a y. Okay? So before we do step 2, I'm going to clean this up. 3x squared times 1 is 3x squared. We have our 6xy, our 3y squared, and our 18. Okay? So step 2, we're going to separate the dependent variables from the other terms, which, as I kind of mentioned earlier, is usually means addition or subtraction, but sometimes you'll see some other things. In this case, the only terms that don't have dy dx's are this 18 and this 6xy. So the 18 is already separated, so let's go ahead and bring this 6xy over by subtracting it to the other side. Okay. Step 3, if necessary, factor out a dy dx. We do have 2 dy dx's, so I am going to factor that out. Which brings me to step 4. I'm going to solve for the derivative, which, as I mentioned earlier, usually means divide. And sure enough, it does, right? These two things are being multiplied. So if I divided this over, we would get dy dx, my derivative, equals 18 minus 6xy over 3x squared plus 3y squared. And then there are 2 other simplification steps that you could do, potentially. Like if it was a multiple choice, you need to be able to recognize them. The first is that all 4 of these terms have a 3 in common. So I could divide those 3's, giving me 6 minus 2xy over x squared plus y squared. The other is a little bit weirder to see at first, but technically speaking, all of these 4 terms do have a -1 in common as well, right? So if you were on a multiple choice part of a test and you were looking at the answer choices and you didn't see this as your answer, or one of these 2 as your answer, it would probably be this one if anything. But if you didn't see that, then you'd be looking at, well, what if they divided the negative out? If they divided a negative out of all 4 terms, this negative 2xy would become positive 2xy. This positive 6 would become negative 6. This negative x squared would become negative x squared, and this y squared would become negative y squared. And so you might look for the answer that has all of the exact same numbers and variables, but every single sign has been changed. Because if you see that, what's happened is that they've divided a -1 out of the top and bottom. Okay? So we're going to do 2 more. I would recommend, since you've kind of heard one walked through and have seen one walked through, I would recommend pausing the video and giving the second one a shot, restarting it when either you have an answer or are stuck and are wanting to verify something. But that's going to be on you. So example 2 here is going to be find dy dx for 3x squared plus y squared minus 6y equals 18. Again, I'd recommend pausing the video, giving this a shot on your own, restarting it when you are ready. Okay, so here you go. dy dx. Step 1, take the derivative. Derivative of 3x squared is 6x. Derivative of y squared is 2y, and then I just took the derivative of y, so it's dy dx. Derivative of 6y is 6. And then I just took the derivative of y, so dy dx. Derivative of 18 is 0. Step 2, separating everything that's not a dy dx from the dy dx's. So my dy dx's are already together, but the 6x needs to go away. So we have 2y dy dx minus 6 dy dx equals -6x. Step 3, if necessary, factor. We do have 2 dy dx's. I'm going to go ahead and factor this one. To then divide. To then solve, which again usually is divide, but potentially something else. And then what else might they have done? Well, there's a 2 in common, so they could have divided that 2 out, -3x over y minus 3. Or they could have also divided out a negative out of everything. So it'd become positive 3x, positive 3, and negative y. Okay. Okay, example 3, this is going to be the last one for this kind of set. Then we're going to throw in a vocab word here. But so if you have not already, I would pause the video and give this next one a shot. Find dy dx for x squared sine 2y equals x. Okay. So step 1, take the derivative. We have two things being multiplied, so that's product rule. We have 1 x squared. d2, we have derivative sine is cosine. Leave the guts alone times the derivative of the guts. Our chain rule there. And then I just took the derivative of a y, so we tack on dy dx. Plus my 2 sine 2y, d1, derivative of x squared is 2x. And on the back, the derivative of x is 1. Okay, I'm just going to clean this up before we do anything else. We have a 2, an x squared, a cosine 2y, and our dy dx. Back here we have a 2x and a sine 2y, and our 1 on the other side of the equals. Okay, separating everything that isn't a dy dx from everything that is means, well, I only have the one dy dx, it's already on this side, so we're good with that. Means moving this one over to the other. Okay, step 3, if necessary, factor. Well, in this case, we don't have two dy dx's, so I don't need to factor. Which means our last step is to solve for dy dx, or divide this component over to the other side. So we have 1 minus 2x sine 2y divided by that 2x squared cosine 2y. And there's really nothing else they could do in this case besides that whole divide everything by a negative bit, which is to turn this into a positive 2x sine 2y, a negative 1, and a negative 2x squared cosine 2y. Okay? Okay, the last two examples that we are going to do here bring back kind of an older idea, which is the idea of perpendicular. We have written a number at this point of tangent line equations, although we're going to do that again. But I wanted to throw in here one more type of equation we could write, which is a normal equation. A normal equation is the equation for a perpendicular line to the tangent line, which means that it has all of the same attributes, all of the same kind of derivative pieces, equation pieces, x and y, coordinates, but to be a perpendicular line, going way back now to a number of years ago when you first learned this, to be a perpendicular line, our slope is going to be an opposite, meaning positive becomes negative or negative becomes positive, and reciprocal, meaning flipping the fraction, slope. That's the only thing that's going to change, is the slope itself in the equation is going to change sign and flip the fraction. Okay? So let's do one together here, and then I'll give you one that you can pause the video and try it on your own for. Okay, we are going to find the equations of the lines tangent and normal to negative x squared y plus 2y equals negative 2 at x equals 2. Okay, so let's do this one together. Let's do tangent first, because tangent's the one we've done quite a few of at this point. So we are writing equations, so we know we are doing y minus y1 equals m times x minus my x1. My x in this case is 2, and then my y, I did not give you the y. I have not always given you the y. So either look back in your notes or think about it. Where did we get that y from when I didn't give it to you before? Okay, and hopefully you're finding it or thinking about it. We get that y as a reminder by taking this 2 and plugging it into my equation. If I take this 2 and plug it in here, we have, let's do this off to the side. I take this 2 and plug it in, we have negative 4y plus 2y equals negative 2, which means negative 2y equals negative 2, which means y equals 1. And then slope, how did we find slope for our tangent line? Again, looking back or thinking about it, we should remember or find in our notes that slope, we got our slope from our derivative. That's what a derivative was. So we're now going to take the derivative of this function. Okay. We see two terms multiplied together, so this is product rule. So we have our 1. d2, derivative of y is 1. And then I just took the derivative of y, so dy dx. Plus my 2, which is my y, d1, derivative of negative x squared, is negative 2x. Derivative of 2y is 2. And then I just took the derivative of y, so dy dx. And derivative of negative 2 is 0. Okay, cleaning this up, we have negative x squared, dy dx minus 2xy plus 2 dy dx equals 0. Okay, separating the dy dx terms from everything else, my dy dx's are already together on the left, so let's move this negative 2xy over to the right, because it doesn't have a dy dx with it. If you did for some reason have a dy dx on this side, you'd want to bring it over to be with the other dy dx's, right? You're getting all the dy dx's on one side, everything else on the other. If necessary, we will factor out a dy dx, which is necessary in this case, to then solve for dy dx, which means to divide over to the other side. And so my slope is 2 times x times y divided by negative x squared plus 2. Okay, well, that means my slope is 2 times, 2 times my x, which is 2, times my y, which is 1, divided by negative my x squared, which is 4, plus 2. 2 times 1 is 4, divided by negative 4 plus 2, or negative 2, gives me a slope of negative 2. And that's my tangent line. Okay. Well, to find my normal, which is our kind of reminder piece here, normal, remember, is a perpendicular line, so everything's the same. The derivative's the same, the x and y coordinate point are the same. The only thing that's changing is my slope itself, this negative 2. To make it normal, I'm going to make it opposite, so change the sign, and reciprocal, flip the fraction. Okay, so everything's the same. We still have our y minus 1 and our x minus 2, but this slope, we're going to change its sign, so it's going to become positive. And we're going to flip the fractions. This is going to become 1/2. And that's a normal line compared to a tangent line. Okay, I'm going to give you one to try now. So after I put it up, again, pause the video, give it a shot on your own. Example 5. Find the equations of the lines tangent and normal to x cubed plus 3xy equals 10, 3xy equals 10 at x equals 1. Okay, go ahead and pause the video, give this one a shot, restart it when you are ready. Okay, so tangent equation, we are doing y minus our y1 equals m times x minus our x1. Our x1 in this case is 1. I didn't give you a y, so we get our y by plugging it in. 1 cubed is 1 plus 3 times 1, or 3y, equals 10, which means 3y equals 9, which means y equals 3. Okay, slope comes from my derivative. So derivative of x cubed is 3x squared. We have product rule here, so 1 is my 3x. d2, derivative of y is 1. And then I just took the derivative of y, so dy dx. Plus 2, which is y. d1, the derivative of 3x is 3. And then the derivative of 10 is 0. So before doing anything else, I'm just going to clean this up. Okay. So separating the dy dx's from everything else means, in this case, subtracting that 3x squared over and subtracting the 3y. And then last step, dividing, we get our negative 3x squared minus 3y over 3x. And you could leave it here and plug in at this point, but I'm going to go ahead and divide the 3's out, simplify it a little bit further. 3x squared, negative x squared minus y over x. So I'm going to go ahead and divide the 3's that they all have in common before I plug in. But you don't have to. Okay, so my slope, m equals my negative x squared, so this would be plugging in 1, negative 1 squared, which is negative 1, minus my y was 3, so it's minus 3, over my x, which is 1, which is negative 1 minus 3, or negative 4 divided by 1, which is negative 4. Okay. And then normal, everything is exactly the same. Everything about a normal is exactly the same, except that my slope is going to be opposite. So the negative becomes positive. Reciprocal means flip it. The 4 becomes 1/4.